So at the end of last week, we had wrapped up our discussion of generic programming in C++, or maybe I should rephrase that. We wrapped up our initial discussion of generic programming in C++. We're going to cover generic programming in a much more thorough way as we ease into the C++ standard template library portion of the course, which is kind of the second part. And if you recall, we went through a half dozen different variations of generic stacks, and I showcased all kinds of interesting different nuances in those implementations. So let's take a quick step back and kind of summarize the pros and cons of what we covered last time, and that'll provide the transition into the next topic. So the generic versions we looked at had all the benefits that we got from the data abstraction versions. So we were able to encapsulate creation and destruction and initialization and assignment and so on. And we also had the ability to generalize by type, which is really the virtue of doing things in that form. We also were able to showcase core patterns and idioms associated with writing exception-safe code, and we're going to talk more about that shortly. So those were the good things, and I think the generic programming features we discussed are very important, and they provide a firm foundation for topics we're going to cover here in the not-too-distant future. But as with all things, there's not always unicorns and rainbows for everything. So one of the downsides with the approach we looked at was the programmers had to remember to call is full and is empty. And you had to make sure you check the results from those calls. And if you didn't, then you'd end up pushing onto a stack and you might exceed its bounds, and failures would occur in bizarre ways. It might throw an exception, it might not. It's kind of hard to say because it wasn't really built to guard against improper use. It expected the stack abstraction up to this point, it expected you knew what you were doing. Now we're going to fix this with C++ exceptions and the C++ exception features very shortly, but that was a limitation with the generic programming technique that we looked at up to this point. That's not a limitation with generic programming, by the way, it's just a limitation with the way I used it heretofore. And then the second thing, and this is a more interesting problem, we can't or we couldn't customize the implementation of our generic stacks at runtime. And we'll talk about this in more detail in a little bit, but bottom line was if we wanted to make changes to the implementation, we'd end up having to recompile and re-implement and possibly break a lot of client code. And we're going to show how to fix this particular problem using the C++ object-oriented features like abstract-based classes and inheritance and dynamic binding. So exception handling, more sophisticated exception handling, and object-oriented programming will be the focus of what we're going to be covering next. So let's use this as an opportunity to transition into the discussion about exception handling. So we're going to take a look at one implementation of exception handling. There aren't that many different ways to do it for what we're intending its purpose here. And so we're going to take a look at the example, and you're going to be able to find that example in my GitHub repository down in the C++ overview capabilities folder in the 5-C++ exceptions subfolder. So what we're going to do now is we're going to take a look at how we can integrate C++ exception handling into the interface of our class such that when errors occur, the user, the client code, will be informed that something's gone awry, and they therefore no longer are responsible for calling full or empty to see whether or not the stack has reached its boundary condition. And before, we'd used exception handling primarily just to make sure that we wrote the strong exception safety guarantees, and we did that using those C++ patterns and idioms to make sure that destructors clean things up. We'll talk a bit more about that shortly, but right now I want to focus more on the usage of exceptions in client code. So in this case, what we're going to do is we're going to modify our stack to throw exceptions when you try to push onto a stack that's full or you try to pop off a stack that's empty. So here's the code. We're using this to report errors, and we're going to define ourselves a stack of int, which will have 10 elements in it. And then we're going to go ahead and write a for each, or forever loop rather, not a for each loop, a forever loop. And this loop will run forever until, of course, an exception is thrown. We also could have written this as while true. So this is another way to write that code. while true and forever will have essentially the same performance. The compiler optimizes them so that they perform exactly the same. So you're welcome to choose whichever one you like. I kind of like the forever loop syntax just a little bit more because it's very clear at looking at it. It's going to run forever. So what we do is every time through the loop, we're going to try to push. And of course, this is going to work for the first 10 items. And then on the 11th push, things are going to go awry. But how will they go awry? Well, let's go look at the implementation and see what it's trying to do. So you can see here that when push is called, the first thing it does is it checks to see if the stack is full. And if the stack is full, it goes ahead and it throws the overflow exception. And we'll take a look at the overflow exception in just a moment. But I think you can imagine the idea here is we have a special designated exception that indicates the stack is full. And we'll look at its implementation. But once it's thrown, then it can't be ignored. And that's one of the things that makes exception handling nicer than returning error codes, which can be ignored in some cases. And you can blissfully think your program is working fine when in fact it's gone awry, but you don't know it. So exceptions make it very hard to ignore. Now, if things go well and we have not tried to push onto a full stack, then we go ahead and we simply push the element onto the underlying data structure. And I'm not going to focus too much on that at the moment. That was what we had covered in the generic programming part. So I want to focus on the exceptions. So let's go ahead and take a look at the overflow exception. So you can see here, here's the stack API that we defined. It's a generic stack like before. In fact, it's pretty much identical to what we had before, with the exception that it throws exceptions. And here's the overflow exception. Overflow is just a class that inherits from the base class exception, and it defines a method called what. And the idea of the what method is to give you a chance to return an indication of what's went wrong, what has happened. And you can see here that what is const, it doesn't modify anything. It is no except, which means it won't throw an exception. If the exception handling method threw an exception, then we'd never get out of the infinite recursion of exceptions that were propagated at that point. And then we're also, of course, overriding the what method, which actually appears in the exception base class. So let's see if we can find the exception base class. Might be, whoops, those are the standard exceptions. Let's not focus on that right now. Bottom line is that there's an exception base class, and maybe I can get it here. Come on. Here we go. So this is the exception base class. And if you take a look at this, you should see that it has a what method, and it's a virtual method, which means that it's intended to be overridden in a subclass. All right, so that's where we're getting the core exception API that we're going to be overriding. And all we say here is we just say overflow exception happened. We just return a string literal that said overflow exception happened. We could probably say something more interesting, but this is good enough for our purposes. All right, so that's overflow. And let's come back to the main program. And you can see that when the overflow exception is thrown, then in this particular case, we immediately catch the overflow exception. So we immediately catch stack int : overflow, and we catch it as a reference. Wouldn't really cost us much to do it by value, but we catch it as a reference. And then we go ahead and we say, here's what happened. And when we run this code, as we will in a second, you'll see that it'll say inner overflow exception thrown or something like that. So that's what happens if we try to push onto a full stack, which of course we will, because we're doing a forever loop here. All right, we'll come back and look at this a bit more in a second, but first let's go through and take a look at what happens when we try to pop on an empty stack. So we then come down here, and of course we push these items onto the stack, and we caught the exception. So the stack now has 10 legitimate items on it, and it hasn't been corrupted because we wrote the code carefully to avoid corruption. And down here, you can see that what we're going to do now is we're going to have another forever loop, and we're going to go through the contents of the stack, and we're going to take a look at the top item each time. And we can get rid of this I here. And we're going to print the top item, and then we're going to pop off the stack. Well, of course, this is also only going to work for 10 runs, because once we pop all 10 items off the stack is now empty. And when we try to pop an empty stack, we're going to get another exception. So let's go ahead and take a look at pop. And here's pop. We say, if the stack is empty, then throw the underflow exception. Otherwise, just decrement the size of the top counter by 1. So let's go take a look at underflow. And I think it'll come as no surprise that underflow is pretty much the mirror image of overflow. It also inherits from the exception base class, and it has a what method, and its what method returns the very insightful phrase, underflow exception happened. So that's how we report what happened when that exception is thrown. All right, so far so good. So now you can see that we'll catch the overflow exception when we push onto a full stack, and likewise, when we pop off an empty stack, we're going to catch the underflow exception. And that will go ahead and also print out a diagnostic. So now that we've all seen this stuff, let's go ahead and run the code, and you can actually see what it does. And as you can see here, it starts out push, 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 push. When we get to the 11th push, the overflow exception is thrown. We catch the overflow exception. We then go and do all the pops. So we pop 9 to 0. And then when we do the next pop, when we try to do the 11th pop, then the underflow exception is going to happen. All right, so far so good. Hopefully that all makes some sense. Now what I want to do is show you what happens if we don't catch the exception when it occurs. So let's say, just for kicks, and I of course would not recommend you do this in production code, but to make the point here, let's go ahead and comment out this stuff here. So now what's going to happen is we're going to do all those pushes, and when we throw the overflow exception, it's not going to get caught here. So the question is, what happens? Does this code get run down here? Does something else happen? And the answer is, it depends on how you've set up your program. So in this case, to make my example interesting, I had another try-catch block, which I call the outer try-catch block, that wraps around this inner set of try-catch blocks. And if you take a look up here, I have catch standard exception. Remember, standard exception was the base class of our overflow and underflow exception. So the rule in C++ is when exceptions are thrown, the compiler immediately starts transferring control away from where the exception was thrown. And it starts looking for exception handlers, these so-called catch clauses. And if it doesn't find one in the context in which it's running, it starts looking up the stack, or up the block scoped stack, if you will. It's not really a stack, but the blocks that are in a method call. And in this particular case, we had a block scope exception handling catch clause, which handled any exception, and in this case, it's the standard exception. And in our case, the overflow and underflow exceptions inherited from that. So we'll actually end up catching this exception here, and then we're going to go ahead and say what happened from the outer context. But when we run the code, you should notice that we no longer call the pop code here because we've jumped over it. So let's go ahead and run the code. As you can see here, exactly as I described, this time we're going to catch the exception, and we know it's an overflow exception because that's what told us, but it got caught by the outer block here instead of the inner block. All right, and if we had method calls or function calls, the same kind of thing would occur. The stack kind of unwinds and it moves up through the different layers until it finally will either find an exception handler or fall off the end of the main program or the thread if a thread is running. And we're going to take a look at that case in a second as well. So what I'm going to do now, just for kicks, is I'm going to go ahead and comment out the outer try-catch block. Let's get rid of that. So now we no longer have the outer block or the inner block. And let's go see what happens when we run the code now. So when we run this code, we now no longer have any exception handler. And what happens is exactly what's intended to happen in C++. If you have an exception that is not handled, it will terminate the program. And you can see here we get an error. This is actually being printed from the the C++ runtime environment, it says, terminate called after throwing an instance of stack int overflow. And then it says what happened. It says the overflow exception happened. So this gives us an indication we have an unhandled exception. Now, there are ways of being able to have something called an unhandled exception handler, but all it does is it can just report some information before the program dies, or it could maybe save some open files or something like that. Bottom line is you don't want exceptions to be propagated out to the point where your program terminates. That's considered very bad style. Something else I do want to note, however, is even if an exception is propagated out of this program, the compiler will still generate code for the destructor of stack S1 such that S1's destructor will be called. So one of the great things about C++ exceptions is that they work together quite nicely with destructors, and as exceptions are propagated out of blocks or methods or functions, as we might say, the objects inside of them that have destructors will have their destructors called, and cleanup can occur. And that's very important because that's the trick that we're going to leverage when we write our exception-safe containers, exception-safe generic containers, or just exception-safe code in general, by ensuring that the destructors clean up the resources that they have been either allocated or handed to own. And this is what's commonly called the resource acquisition is initialization idiom in C++. So that's why we have things like unique pointer. That's why we have things like scoped array. That's why all the STL containers all have destructors that clean things up, because if exceptions occur, we want to make sure we don't leak resources. Okay, so that was, in essence, the way that you write code that uses exception handling. And now let me go ahead and clean up this code so that next time I talk about this, it's not all littered with stuff commented out. Let's see if there's anything else I forgot to tell you about exception handling. Again, the key point was that this was about throwing exceptions and then having client code catch the exceptions. We'd already had all the other cool exception handling stuff put into this from our previous discussion about generic programming. You'll notice I have our unique pointer here. You'll notice in the .cpp file, in this case, I'm using new. I probably should be refactoring this to use unique pointer or make unique pointer and all that kind of good stuff. But that's left as an exercise to the reader if you're incentivized to go ahead and do those kinds of changes. But this code works, it's exception safe, and now it properly throws exceptions. All right, so let me see if I can switch over to my slides, and I'm going to bring up my slides. If for some reason you cannot see my slides, please let me know, because that means something weird has happened. So what I want to do is just kind of briefly summarize the issues associated with exception handling. Now that you've kind of seen the full kit and caboodle, let's take a step back and look at this whole process in a more holistic way. So it turns out when you write exception code, there's several types of guarantees or assurances you can provide. And you really want to read this article, Exception Safety, for more discussions about these different guarantees. So the first kind of guarantee is no guarantee. You might call this the caveat emptor guarantee. It means let the buyer beware, let the program beware. And what no guarantee semantics mean is memory can be leaked if an exception is thrown, invariance of a component may not be preserved or will not be preserved. Basically, it means chaos and insanity are going to reign, which is not a good thing. And we saw this kind of a problem when we had talked about the C++ data abstraction implementations earlier in the course. So if you take a look here, you can see that here was the Simon operator for one of our earlier stack implementations that was in fact not thread safe when parameterized by type T. So that's a bad thing. Don't do that. Do not write this kind of code. The second form of guarantee is to add some kind of basic guarantee. And all that really means is that I pledge on my Scout's honor that I will not leak memory if an exception is thrown. So here's an example of that. This is also something we had taken a look at when we were talking about the C++ templates, I kind of talked about how you could put try catch blocks in there in order to be able to catch exceptions and then delete the memory. Now, this isn't a bad approach, and in fact, this is often kind of the core level exception guarantees that most people come to know and love. So if for no other reason, get accustomed to writing basic guarantee code, basic exception safety guarantee code. But we can do better, and it turns out it's not very hard to do better. In fact, we can actually do a lot better. We can do what's called strong exception safety guarantees. And what these guarantees say is either the operation completes successfully and all is well, or it throws an exception. And if it does throw an exception, the state of the program is left in exactly the same state it was before the exception was thrown. I like to call this the Hippocratic oath of exception handling, which says, do no harm. So don't go ahead and make your code have weird side effects where you don't leak memory, but you leave things in an inconsistent state, because that's bound to irritate your users, unless all they're going to do when an exception is thrown is just bail out of the program, which is also a feasible thing to do. But if you're really trying to write exception-safe containers, especially generic containers like the ones we have in STL, you probably don't want them corrupted as a side effect when an exception occurs. So here's, of course, the way to do this. We've talked about this a number of times. The way to do it is to define an exception-safe copy constructor, and then define a no exception swap operation, and then implement your assignment operation, your copy assignment operation, in terms of the exception safe copy constructor and the no exception swap operation. And I think you'll agree with me that this code is very short, and the cool thing about it is it's perfectly exception safe, it's strongly exception safe, and the best part about it is that you don't have to put a try-catch block anywhere. It handles everything using the wonderful feature of C++ destructors, that they will clean themselves up even when exceptions are thrown. So that's really, really cool. Then the fourth type of guarantee, really the third real guarantee, the first guarantee is more like a joke, the no guarantee guarantee. The final guarantee is the so-called no-throw guarantee. And what this says is this operation or this method does not and cannot throw an exception. And again, I pledge on Scout's honor not to let it throw the exception. And the way we've seen that so far is by making sure that our swap method, making sure that our move constructor, making sure our move assignment operator all are marked as no except. And then, of course, we have to make sure the code is written in a way that won't throw exceptions. And that's a flag to the compiler that this code will not throw exceptions. And that allows certain optimizations to be done. More importantly, it gives you assurance as a person using this class that you understand the semantics of how the class was devised. And it's also usually a good sign that the person who wrote the class actually knew what they were doing, which is a good thing. So we've seen no-throw semantics as well. So armed with all the information about exceptions, now let's take stock of what we've covered. So as we've seen, the exception handling techniques that we discussed make it possible to have a very canonical, disciplined, pattern-centric way of dealing with runtime problems by rigidly decoupling or separating the error handling code from the normal code. So the normal code goes through one path, and if all goes well, we're happy and fine. But if an exception condition arises at runtime, we have these exception handling catch clauses that can be nested so that those things will be handled properly. And another nice thing that exception handling does, especially for C++, is it makes it possible to cleanly handle errors that occur in constructors. So when constructors throw an exception, there's a way to clean up on that, and there's a way to know that. Whereas in previous versions of C++ prior to exceptions, back in the Wild West days, people had to do all kinds of crazy things in constructors to deal with the fact that they couldn't throw exceptions. Now again, as I always like to say, everything is not unicorns and rainbows. So a couple of issues to realize. First of all, exceptions can be very tricky to program correctly if you don't understand the patterns and idioms that we've discussed, because you'll end up with resource leaks, you'll end up with corruption, and so on. The good news is once you've understood those patterns, then life is going to be much easier for you. And that's what I've been conveying in the course. And you'll get a chance to practice that in some upcoming assignments. The other downside, which is becoming less of a problem as compilers get smarter, is that there is potentially some increased time and space overhead for programs that use exceptions, because they have to put in exception handling mechanisms, and there's many different ways to do it. Typically, the different ways of implementing exceptions either end up making your program bigger, but perhaps still very fast, or smaller, not smaller, but not as big, and be a little slower. And modern C++ compilers, of course, optimize the heck out of this, but just have to be aware that exceptions don't entirely come for free. But the pain is almost always worth the gain in most normal situations.